So, two dopants, potassium, iron oxide. Then we go and we test particle strains. We take individual particles after they're sintered and we squeeze them in an Instron machine and we measure the load to failure and hence the stress, the tensile stress, which will be right in the middle of the particles at which they break. And we relate that to American Petroleum Institute tests, tell us whether or not it should be a good problem. Right? This is what we get. This is state of the art. That's considered, that's carbo HSP, high strength proppant. That is the state-of-the-art material out there right now. It's comparable to state-of-the-art stuff. That's 10 weight percent iron oxide. That was synthetic. 10 weight percent impurity in your material. Would you have heartbeat with that? Or heartburn with that? Okay? So what we told them was deliberately add impurities. Deliberately add dopants. So we can see what its effect it has so that you can go out and you can buy chromium ore as your raw material to make a better product. Okay. So the end result was, if we know something about thermodynamics, if we know something about kinetics, if we know something about the role of microstructural evolution on strength, we can tailor virtually any material to behave and give us a good problem. The work of sintered bauxites and kaolins, drill cuttings are going to be the same way, but we came up with a few more surprises. This one blew us away. We should have known about it. All right? If you look at this microstructure right here, what you're looking at is one proppant particle that was sintered to full density, i.e. no porosity. And then by changing the oxygen fugacity, partial pressure in the sintering furnace, we re-evolved porosity. We decomposed the iron oxide to a different form of iron oxide of different valence state, giving off oxygen, which in turn crept the ceramic microstructure, leaving behind bubbles. This is a malted milk ball that started dense. Okay? The other thing about it is that dense particle after sintering was decorated both internally and on the surface with our zero-valent dopant. In this case, iron. It could be titanium, it could be some other transition metal. They're catalytic. So now we got a proppant particle that's dense with a catalytic surface. It might possibly be useful to us in situ treatment of hydrofracturing fluids, right, which also wound up getting patented, right, as part of the core shell patent. We can make them malted milk balls that have a dense outer rind, porous interior. We can tailor the degree to which it's a malted milk ball with time, temperature, and oxygen partial pressure. We can make these float, yet still exhibit a strength of over 300 megapascals. Remember, 250 megapascals is the state-of-the-art proppant. Why is that important to us? If we can tailor the specific gravity, we can change the hydrofracturing fluid composition significantly. We can get rid of some of the things that we add as surfactants and dispersants and suspenders, because the stuff is about the same buoyancy as water. You can put it where you want it without having it settle out in the region of your well. That's really desirable to the hydrofrac industry. Some of the additives in hydrofracturing fluid, did we ever hear about them in the newspaper? We hear about their potential effects, right? But no one ever tells you what they use. Well, I can tell you what they use. I know a lot of stuff they use, right? And so do they, right? So the bottom line is, if you can use less of some of that stuff, maybe you'll have less of a concern with the hydrofracture, okay? And if you can treat what's down there with a catalytic surface on your proppant, you don't have to treat the water as severely when it comes to the top after you've hydrofracked, because you have to remove your water from your hydrofrac well, at least some of it. Okay, you get about, what, 40% flow back these days, 20%? Okay, so the bottom line is, by messing around with our material science, our phase equilibrium, our kinetics, our microstructural evolution, we come up with ways to make products that will outperform the current state-of-the-art stuff with materials that aren't as good as what you wanted to start with and that you were paying big money for, okay? And you're making a lot of them. This will give you an idea of the magnitude to which we can do that. These both started completely dense, no porosity. After 4 minutes and 64 minutes at 1550 degrees C, by changing our oxygen partial pressure, we created gas bubbles that formed this Swiss cheese malted milk ball effect with a dense outer rind. And when you look at the activation energies associated with the evolution of that microstructure, they are almost exactly coincident with the activation energy for creep of aluminosilicate brick, done by Dick Brott in the 70s. Okay? So we know why these are forming. We know how fast they're going to form, and we can tailor our process and chemistry to be able to manipulate that. Okay? And going from the dense, metallic, decorated surface with heat treatments in air, we can turn an outer rind into an iron-containing aluminosilicate while at the same time having entrapped iron, metallic iron, Fe, zero valent, in the interior, which, for those of you skilled in the art of mechanical properties of ceramics, is a ductile phase toughening agent. Fracture toughness of that material will be significantly higher than that material. Okay? These are the things we manipulate. And just to give you an idea that this should be something that gets your attention. That bead floats. Okay? It has effective specific gravity of less than 1. And it's because it's a malted milk ball. Dense outer layer, porous inner core. Still high strain. A couple of 100 megapascals. Okay? All right. That's bauxite. That's kaolin. That could be drill chips. All right? Why are drill chips important to us? You drill a well, you got to do something with the chips. The chips contain norms, naturally occurring radioactive materials. So it's considered a residual waste that has to go to landfill under controlled circumstances. It costs you money to get rid of your drill chips. If we can use drill chips as our starting raw material, we're putting them right back down the same well or some similar well someplace. All right, we solve a couple of problems all at once, so we're funded to do that work as well. But then we said, okay, what if we didn't want to mess around with bauxite or kaolin? What if there was another raw material source available that we could use to our advantage because it's plentiful, it's close by, and it has about the right chemistry for us to be able to manipulate as material scientists? And the ones we chose were aluminosilicate materials that come out of the result of mining operations. This happens to be some powders of a material that is thrown away to the tune of 1 million tons per year in Pennsylvania. I'll pass that around. All right. Or, what about glass? We have a domestic recycling stream. We've been trained to do this. Your clear glass goes into new bottles. Your brown glass and your green glass don't go into new bottles at as high a volume fraction. As a matter of fact, a lot of the brown glass is thrown away or put into low value added products like abrasives. Because it's difficult to make new glass out of that. You have to control your chemistry carefully to get the right brown and not have compositional discontinuities that wreck the properties of the bottle. All right? So there are companies that recycle glass all over the United States. Massive, massive quantities, low cost, readily available, ubiquitous to any region you want to talk about in the United States, except maybe Alaska. All right? And you got a raw material stream there. But glass doesn't work. Okay? Glass beads have been tried before as problems. Glass beads are readily available. There's a huge industry that makes glass beads for things like abrasive media and additives for reflective paints. So the technology's there to make these in the quantities we need. But when you put them down a gas or an oil well and the closure forces start stressing the beads are so strong because of the way you made them that there's so much stored elastic strain energy in them that when they do break, they blow apart into dust. And that dust clogs the interstices between the other beads and your permeability goes down. All right? So the longevity of that propped well when you use glass is not very long. So we have to find a way to alter that fracture behavior such that it doesn't fail into fine particles but fails into bigger chunks. All right? Well, one way you can do it comes out of other work that we did at Penn State over the years on tailored residual stress profiles in glass. All right? What you're looking at here is this circle is a hole in a piece of paper that we put one proppant particle into and then squeezed it to failure. So these are the fragments remaining from that proppant particle blowing up when we broke it. This is glass. This is something that's not glass. This is a glass ceramic that we're manufacturing in proppant form. We want this, type 1 failure. We don't want this, type 2 failure. These blind the interstices and decrease permeability. These still prop. Okay? How do you do it? Well, in the glass case, we said, I'll tell you about the aluminosilicates first. So in the aluminosilicate case, we said, fine, use those mine tailings that are going around here someplace, that green stuff, manufacture glassy beads out of that using a flame spheritization process, then using what we know from 80 years worth of glass ceramic research, devitrify that glass to give you the right crystalline phase assemblage and microstructure to increase the fracture toughness of that bead to the point that it fails into big particles. Well, we can do that with the materials that are mine tailings because they have the right alumina-silicon ratio as well as the alkaline and alkaline earth content for us to have a pretty good idea where we have to heat treat this stuff to make glass ceramic that'll have some altered mechanical properties. So we spent 4 years, 5 years doing that, understanding devitrification behavior of aluminosilicate melts. These are lava. This is obsidian. This is our synthetic obsidian from that material. This is lava-based materials that in our particular case, after deposition due to the application of heat over long periods of time in their geological strata, metamorphized back into rock. Well, if you control that devitrification process, which we do with our furnacing, you can control what crystalline phase comes out, how much of it comes out, and what shape it is, and how it's interconnected, which in turn then interacts with any crack that will propagate through the material, increasing the fracture toughness, thereby causing the stuff to fail like that instead of that. Okay? That was the whole approach, so we did that. First, we built the flame spheritization tower. So this is about a 7-foot long silicon carbide tube with oxyacetylene torches. We feed the glass through in fiber form. We make the glass to begin with. And then we spheritize it to form little balls. Here's some of the product. Falls out the bottom into a nice Tupperware container. And then you have a graduate student separate them out bead by bead for testing. So you're manufacturing about 30 cc's of material to do a whole PhD project. Okay, is that pretty good, Dan? Pretty fair? Maybe 100 cc's. But you separate each and every one of these particles out, get them all in the right size range, and do your mechanical testing and your heat treatments. We also do work on the fused materials as fused. They're useful for things like the TTT diagrams and whatnot. And that's important because we want to know how the microstructure evolves as a function of temperature and time. What percent transformation of different crystalline phases do we get as a function of heat treatment? And how does it interact with the crack to crack, deflect, and increase fracture toughness? Classical ceramic science. Okay? Classical geochemistry.